two books which are the basis of several talks given in the lecture. And the first one is a singular introduction to algebraic geometry or to algebra. And that is a book together with Gerhard Krull. And that is, I think that is in the library here. And the second one that does not appear yet, but I could provide it to the organizers that everybody can download it, is algebraic geometry in applications. So and that is together with Wolfram Decker. So of course I cannot prove today everything which I want to explain to you, but the omitted proofs can be found in one of these books. So the title of this talk is Dimensions. So the question is, what is dimension? So let me give this as an example. If you have the plane, then this is something which you expect to be two-dimensional. So, and what is the idea about dimension? You have a subvariety, which is a line that is one-dimensional, and on the line you have a point which is zero-dimensional. So point, line, plane, that makes dimension 2. So if you translate it to algebra, then the plane corresponds, you have the zero ideal in the polynomial ring, and for instance here you have the ideal generated by x, and here you have the ideal generated by x and y, and that is strictly contained in the polynomial ring in two variables over the field k. And so if you denote this by p0, it is a prime ideal in the polynomial ring. This by p1, that is another prime, and this by p2. So the length of this chain is by definition 2. So you get again dimension 2. So that is the basic idea, and now let's do it in general. We take any ring A. So a ring, if I am talking about rings, they are always commutative and Noetherian for us. So, and to such a ring, I associate chains C of A. That is a set of all such chains of primes. So pi prime and consider, as in the example, all these chains, and the length of this chain is k by definition. And then I define the dimension of the ring A to be the maximal length of such a chain, and since it may be in general also infinity, I define it as a supremum of the length of, so I give this chain a name to make it easier. I call this P of P with P and C of A. So that is a dimension. So, or one possible way to define the dimension. And this is also called the Krull dimension. Maybe I write it here. So let me give some examples. So for instance, we have a polynomial ring then we have one chain 0 in x1 in the ideal generated by x1, x2, and so on. Ideal generated by x1, xn. So we have a chain of length n. And one can prove that in the polynomial ring, or also in the polynomial ring divided out by some ideals, all maximal chains have the same length. In A, or more general, K x1 up to xn divided out by some ideal, all maximal chains have the same length. And so then that means the dimension of the polynomial ring is n, as we expected. And let me take a second example. We take A to be the polynomial ring in 3 variables, so let's say x, y, z, divided out by the ideal generated by x, y, and x, z. So So what does it mean geometrically if we want to see the zero set of this ideal? So we are in 3 space, and we have x equal to 0. That is one variable 0. That is a plane. And if we have, on the other hand, if x is not 0, then the 0 that is y comma z equal to 0, and that is a line. So that is the 0 set of the ideal xy comma xz. Then, of course, looking at the geometric picture, the dimension should be 2 because of this plane. And later on, if I will have time, I will also talk about local dimensions. So if I look for the dimension at that point, then it will be 1. And if I look at the dimension at the point here, it will be 2. So why is the dimension now 2? So we have this ideal x, y, x, z. And then we have possible chains, namely the chain x contains this ideal, and then we have the chain xz, and we have xyz. So that has length 2. And then we have, of course, another chain. So this chain corresponds to the plane. Now we have also a chain corresponding to the line. That means xy, xz is in y comma z, and that is in xyz, and that is length 1. So as we defined the dimension to be the maximal length of a maximal chain, we take this chain and we have dimension 2. So this is an example. So now we will see some properties of the dimension. So, and what I will use now is a well-known theorem from commutative algebra, the so-called going up theorem. This says the following: I have B contained A finite extension of rings. So that since B is a ring over A, B is also an A module. And finite means B is a finitely generated A module. Okay, and then the claim says the following: if I have, so I have here A, and I have here B, and I have in A 2 primes, and I have in B a prime Q. So P prime and P and Q primes, prime ideals. With a property that Q intersected with A is P. And then going up theorem says, in this case I can find a Q prime here, this Q prime intersected with A is P prime. So there exists Q prime and Q. So let me do it like this. Such that Q prime intersected with E is P prime. So this is a going up theorem, and that I'm not going to prove, but this you can find, for instance, in the singular book, but in almost every book about commutative algebra. And that we will use now to prove that, so the proposition is B over A finite implies the dimension of B is equal to the dimension of A. Yes?
Can you summarize the statement of the theorem again, please?
Sorry?
Can you summarize the statement of that theorem again from the start?
This year? Yeah, okay. Okay, so you have B and A a finite extension. Forget about the red stuff here. The red stuff is what will exist later on. So, and then the assumption is that you have 2 primes in A, which are contained in each other, and a prime in B, which has a property that the intersection of this prime with A is P. So that gives P, and here you have a pre-prime. And then going up says, in this situation you can find a Q prime between Q and B, such that the intersection with Q prime and A is P prime. That is the theorem. And now let me just give a proof that this is true. So, proof. So A and B finite, and so we have a chain. We have a map from C of B to C of A, namely defined by Q and B prime goes to Q intersected with A. So, of course, if Q is a prime ideal in B, then Q intersected with A will be a prime ideal in A. And if I have a chain of primes then this mapping gives you a map from the chains. So that defines this mapping. And this is surjective. And that's the reason that it is surjective is going up. So that's why I explained going up. Namely, if I start with a prime in A, I could always construct a prime in B. So what we have to show that in case, so that is that the length of the chain does not change. Okay. Now, to do this, let Q contained in Q prime contained in B and Q intersected with A is equal to Q prime intersected with A. And we have to prove then Q is equal to Q prime. So that, and if we are able to prove this, then the length of the chain stays the same. So we call this P. So we have the assumption at the beginning was A and B is finite. And this implies, if I pass to the localization, that BP in AP is also finite. So just to recall, if I denote by S A minus P, then AP is a set of all A divided by B with B in S. And similarly BP. And so I have this finite extension, and then of course I have Q BP is contained in Q prime BP, and the intersection Q BP intersected with AP is the same as Q prime BP intersected with AP. So, and this is, of course, PAP. And PAP is a maximal ideal in AP.